Is your idea of the Big Bang a colossal explosion at a specific location in space? Many popular notions about the universe's origin are actually widespread myths. In this audio guide, I'll dismantle the most prevalent misunderstandings surrounding our cosmic beginnings, blending precise explanation with a lighthearted touch. Let's delve into what scientific evidence truly reveals about that pivotal first instant, and what mysteries still lie beyond our grasp. Grasping the true importance of the Big Bang is the first step, because this isn't merely a tale from the distant past. It's the fundamental framework for understanding our present-day cosmos. While many picture a cosmic firework bursting in the darkness, I want to show you that the reality is profoundly different. The Big Bang isn't a story about an explosion at all, but rather the continuous unfolding of everything from a state of infinite density into the sprawling universe we inhabit today. At its heart, the Big Bang theory presents a universe in a perpetual state of change. A useful analogy is to think of an inflating balloon. Initially compact, it grows larger as more air is introduced, just as our universe has been stretching ever since its inception. This expansion is not mere conjecture, it's a fact supported by direct astronomical evidence. The proof lies in the light from faraway galaxies, which is stretched toward the red end of the spectrum, unequivocally signaling a cosmos that is constantly moving apart. Any discussion of the Big Bang inevitably leads to the concept of the initial singularity. So what exactly is that? Try to conceive of a state so incredibly hot and dense that it pushes the boundaries of human comprehension. At time zero, the entirety of existence was compressed into a space of zero volume. The true nature of this moment is still an enigma, fueling our deepest questions about how existence could arise from apparent nothingness and what transpired in those first infinitesimal fractions of a second. Another critical piece of this puzzle is cosmic inflation. Very shortly after the Big Bang, the universe experienced a period of exponential expansion, far faster than its current rate. This wasn't a steady, leisurely process. It was an almost instantaneous surge, ballooning in size in an unimaginably small fraction of a second. This inflationary epoch is crucial because it accounts for the remarkable uniformity we observe across the cosmos on the largest scales. The theory also describes a fascinating event, the simultaneous creation of matter and its counterpart, antimatter. In the universe's nascent moments, the fundamental particles that constitute everything from galaxies to you and me were forged. However, this process presents a lingering enigma that scientists are actively working to unravel. Why did a slight surplus of matter survive to create the universe we see, while antimatter all but vanished? Then, there is the process of primordial nucleosynthesis. During the initial few minutes of the universe's existence, the intense heat and pressure allowed for the formation of the very first atomic nuclei. The lightest elements, primarily hydrogen and helium, were created in this cosmic furnace, providing the raw materials that would eventually form stars, planets, and even us. The precise conditions that allowed this to happen speak to the elegant and intricate physics governing our cosmos. A critical piece of evidence for all this is the cosmic microwave background, which you can think of as the residual heat or afterglow from the Big Bang. This faint, pervasive radiation fills the entire sky and was famously discovered almost by chance. It provides us with a snapshot of the universe when it was just a few 100,000 years old, a faint echo from the dawn of time that carries the story of our origins. This brings us back to one of the most stubborn misconceptions, that the Big Bang was a detonation happening somewhere in the void. The truth is far more profound. It wasn't an explosion in space, it was the expansion of space itself. Rather than a cosmic bomb going off, you should envision the very fabric of reality stretching in all directions. This distinction is absolutely fundamental to understanding our cosmic origins. Throughout this entire cosmic story, gravity has acted as the master sculptor. From the moment of the Big Bang to this very day, it has been the dominant force shaping the universe's development. Gravity is what pulls matter together to form galaxies and what keeps star systems in stable orbits. Our universe would be an unrecognizable, featureless void without its persistent influence. As we probe deeper, we encounter even greater mysteries in the form of dark matter and dark energy. While these phenomena remain invisible and their nature is a complete puzzle, their effects on the cosmos are unmistakable. In fact, the accelerating expansion of the universe points to powerful forces at play that are beyond our current scientific comprehension, leaving us to wonder what discoveries about them lie ahead. Our exploration eventually brings us to the very edge of what we can know. The Big Bang model gives us a powerful framework for the universe's beginnings, but our telescopes can only see so far, defining the boundary of our observable universe. This naturally leads to compelling questions about what might exist beyond that horizon, in regions of space whose light has not yet had time to reach us. The history of the universe since the Big Bang is one of constant transformation, as the initial simple particles gradually coalesced into the intricate structures we see today. This cosmic evolution produced everything from vast galaxy clusters to enigmatic black holes, all participating in a grand cosmic ballet. The life cycles of stars are woven directly into this history, as their deaths in brilliant supernovae forge heavier elements, seeding the universe with the materials for new stars, planets, and life. This brings us to the final question. What is the ultimate destiny of our universe? The various scientific scenarios for the cosmos's future, whether its endless expansion or an eventual collapse, are all intrinsically tied to the initial conditions set by the Big Bang. Contemplating these possibilities encourages us to consider our own position within this immense and unfolding narrative. As we explore this incredible subject, it's crucial to see the Big Bang as more than a scientific hypothesis. It represents a journey back to the very source of all that exists. My aim has been to clear away the myths and provide you with a more accurate picture, helping you to grasp the theory's true importance in our ongoing mission to comprehend the cosmos. The Big Bang model remains the most powerful explanation we have for our origins, yet it continually pushes us to ask, what did it all truly mean? To properly understand this, it's vital to recognize that the Big Bang was not an explosion in the way you might imagine a bomb. Instead, it describes the very genesis of everything we know, the moment that gave birth to time, space, and all matter. Imagine you are inflating a balloon. As it fills with air, every point on its surface stretches away from every other point. This is a powerful analogy for our universe, which, from its earliest moments as a fantastically dense and compact point, has been expanding and cooling to form the cosmos we see today. A common misconception is that this was a blast that propelled everything outward from a central point. However, the theory actually proposes that no such center exists. The universe isn't expanding from a particular location. Rather, the expansion is happening everywhere at once. Think again about the surface of that inflating balloon. Every spot moves away from every other spot simultaneously. In the same way, every region of space in our universe is moving away from every other, showing that space itself is stretching. This naturally raises a profound question. What existed before the Big Bang? According to current theories, time and space as you and I understand them simply did not exist prior to this event. The laws of physics as we know them break down in that initial singularity. In a very real sense, asking what came before the Big Bang is as nonsensical as asking what lies north of the North Pole. The question itself is based on flawed premises. The Big Bang theory also provides an elegant explanation for the evolution of the cosmos. As the universe expanded, it also cooled, which allowed subatomic particles to begin forming. These particles then combined to create the first atoms, hydrogen and helium, which are the foundational elements from which all stars and ultimately planets are built. This framework allows us to trace the lineage of the universe from its first fractions of a second to the complex structures we observe now. But how can we be certain that the Big Bang actually happened? One of the most decisive pieces of evidence is the cosmic microwave background, which is effectively the faint residual heat from the creation event itself. This radiation, like an ancient echo from the early universe, fills all of space and has been meticulously measured by numerous experiments. Scientists have found that its characteristics match the predictions of the Big Bang theory with astonishing precision. At its heart, the theory demonstrates that the universe is not static, but is instead a dynamic and ever-changing entity. This reality of ongoing expansion leads to another fascinating inquiry. What is the ultimate fate of the universe? The theory suggests several possibilities, from a final collapse known as the Big Crunch to an infinite expansion where the cosmos grows progressively colder and more desolate. The future of everything hinges on this continued expansion. One aspect that is frequently overlooked is how the Big Bang fundamentally shapes our understanding of time. We tend to perceive time as a linear and constant force, but the theory reveals that time is intrinsically linked to the very existence of the universe. Without the Big Bang, time as we experience it would not exist. So every time you look up at the night sky, remember that you are not just seeing stars, but the direct consequence of the event that created reality itself. While the Big Bang is the overwhelmingly accepted model, it's worth noting that it hasn't gone unchallenged. Alternative ideas, such as the steady-state theory, have been put forth over the decades. Yet this scientific consensus did not emerge overnight. It was forged through decades of intense debate and observation. The scientific community has ultimately found that the Big Bang provides a framework that consistently withstands the most rigorous scrutiny. It's crucial for you to see the Big Bang as more than just a single moment in the distant past. It is a comprehensive framework that helps us study the entire evolution of the cosmos. Without this theoretical foundation, many essential questions about the formation of galaxies, stars, and planets would remain completely unanswered. It provides the necessary context for understanding our own place in the boundless history of the universe that preceded us. In conclusion, the Big Bang not only signifies the beginning of everything, but also serves as our window into the vast history of the cosmos. This theory invites you to reflect on our origins and our future, offering a unique and powerful perspective on the nature of time and space. By understanding the Big Bang, we are not only unraveling the mysteries of the universe, but also delving into the deeper questions of who we are and where we came from. I want to take you on an expedition into the past, all the way back to the very first moments of our universe. This journey naturally makes you wonder about the universe's ultimate fate. If its expansion continues, does it have a final limit? Some models predict this growth could eventually slow, stop, and then reverse into a big crunch, causing all of existence to collapse back into a single point. Conversely, other theories argue the expansion will accelerate forever, pushing galaxies further and further into the void. I must admit, we don't have the complete picture yet,
but every new piece of data brings us closer to solving this cosmic puzzle.
The universe's expansion also deeply affects how you understand gravity. While gravity works to pull galaxies together, the stretching of spacetime itself acts as a counterforce, carrying them apart. This poses a critical question that cosmologists are working tirelessly to resolve. Will the force of gravity ultimately prove strong enough to win out over this expansion? The answer remains a key piece of the cosmological puzzle that we are still trying to assemble. Another profound mystery is how this cosmic expansion connects to dark matter and dark energy. You can't see dark matter directly, but its gravitational influence on the movement of galaxies confirms its existence. Dark energy, by contrast, seems to be the very engine driving the acceleration of the expansion, acting as an unseen force that compels the universe to grow at an ever-increasing rate. But for you to truly grasp this, you have to ask, what exactly is dark energy, and will we ever manage to comprehend its nature? As our exploration of the cosmos continues, you come to realize that the visible universe is merely a tiny fraction of what is truly out there. The vast majority of the cosmos is composed of matter and energy that we are unable to detect directly. This reality forces you to consider if there might be other fundamental forces or components of the universe that we have yet to even imagine. The answer is almost certainly yes, as science is a continually evolving process where each discovery reveals new, uncharted territories. The unending expansion of the universe also compels you to reflect on your own existence within this grand scheme. When you truly contemplate the sheer scale of the cosmos, it's almost impossible not to ask what your place is in it all. You are part of an immense ocean of galaxies, where every star, planet, and living organism has its own unique story, reminding you that you are connected to something immeasurably larger than yourself. In this grand context, you must appreciate that the expansion isn't a static event, but a dynamic process that has been unfolding for billions of years. With every passing second, the universe stretches a little more, and our comprehension of it grows a little deeper. Each breakthrough we achieve only leads to new questions and pushes us toward new horizons in our relentless pursuit of knowledge. The concept of an expanding universe has completely reshaped our cosmological worldview, allowing you to perceive the cosmos not as a static backdrop, but as a living, evolving entity. This idea presents you with a fresh perspective on time and space, inviting you to ponder the future of existence in ways that were previously unimaginable. As you delve into these mysteries, remember that every solution we find is simply the gateway to the next enigma. What truly happened at the instant of the Big Bang, at time zero? To approach this, you must confront the idea of the initial singularity, a state where the known laws of physics completely break down. Try to picture a point smaller than any atom, where all the matter and energy of the universe were compressed into an infinitesimal volume of infinite density and unimaginable heat. This is what scientists refer to as a singularity. The singularity defies all of your everyday intuition and experience. We are used to objects that possess distinct sizes and shapes, but such concepts are meaningless when describing the singularity. It is akin to imagining a point where space and time do not exist, where the dimensions that define your reality simply dissolve. How could something so minuscule contain the seeds of everything that exists today? This remains one of the most profound questions you can ask about our origins. The initial singularity represents the very beginning of time itself, which makes it nonsensical to ask what came before the Big Bang. Prior to that moment, there was no space, no time, and no matter, absolutely nothing as you would understand it. This concept stretches your mind to the absolute limits of its capacity, taking you to the very edge of what is comprehensible. Emerging from this singularity, the universe began to inflate at a speed that is difficult to fathom. To help you visualize this, think of a deflated balloon. As you blow it up, every point on its surface expands away from every other point. In the same way, the universe started expanding not from a single location in space, but simultaneously from every point within space itself. This is the foundational idea you need to grasp to understand cosmic evolution. The existence of the singularity also leaves you with a captivating riddle. What force or event could have possibly triggered this monumental explosion of energy and matter? Some physicists propose that our current laws of physics are inadequate and simply do not apply to the conditions within the singularity. This is uncharted territory for science, a frontier that challenges even our most robust theories and invites us to explore what may lie beyond our current understanding. One of the most enthralling aspects of the singularity is that it was the crucible from which everything you know was born. From the simplest subatomic particles to the most complex galactic superclusters, the entire tapestry of existence unfolded from this single, explosive origin point. Every element and every structure in the cosmos traces its lineage back to that initial burst. You can think of the singularity as the very seed from which our universe sprouted, where everything we see began its long process of development. This idea of growth is fundamental to the field of cosmology, as the expansion of the universe triggered profound changes. As energy converted into matter, particles started to coalesce, forming the first atomic nuclei. So, you might ask why it's so vital to comprehend the singularity. The reason is quite straightforward. Our entire existence, along with everything we have ever known, stems directly from that initial moment. To understand the singularity is to unlock the very first page of an epic narrative that has been unfolding for billions of years. The singularity is not merely a starting point. It also serves as a stark reminder of the current boundaries of our scientific knowledge. Science progresses relentlessly, and concepts we accept as truth today could very well be overturned by the discoveries of tomorrow. The singularity embodies these frontiers, reminding us that there is still an immense amount to uncover in this vast cosmos. Let's take a moment to consider how this initial singularity connects to our own experiences. In the same way the universe began from a simple state and blossomed into an intricate web of galaxies, stars and planets, our own lives can start from humble origins and evolve in completely unexpected directions. The universe's history encourages you to contemplate your own singularities, those pivotal moments where everything has the potential to shift. As you and I venture deeper into the study of the Big Bang, it's essential to appreciate that the pursuit of understanding is just as meaningful as reaching the final answer. The singularity shows us that acquiring knowledge is a perpetual journey, where every solution we discover only paves the way for new inquiries. Each breakthrough in cosmology brings us a step closer to grasping our own place within this immense and enigmatic universe. Welcome. If this exploration of the cosmos fascinates you and you wish to continue investigating its mysteries, I invite you to subscribe and activate notifications. Now, as we delve into the compelling story of the Big Bang, we must tackle a concept that completely transformed our understanding of the universe: cosmic inflation. What exactly is it, and what makes it so incredibly important? This phenomenon describes an exceptionally brief but monumentally important era just after the Big Bang, during which the universe experienced an exponential expansion at a rate far exceeding what we observe in the present day. To help you visualize this, imagine blowing up a balloon. At first, the balloon is tiny, almost negligible. But as you force air into it, it expands with astonishing speed, becoming much larger in a mere instant. Cosmic inflation operates on a similar principle. But instead of a balloon, you have to picture the entirety of space itself. In its earliest moments, the universe was of a scale so small it's difficult to even conceive. Then, in just a fraction of a second, it ballooned to an unbelievable size. Have you ever considered what could have possibly powered such a rapid expansion? Scientists theorize that it was propelled by a unique form of energy that saturated the early universe, which they call inflationary energy. This energy functioned like a powerful engine, driving the fabric of space outward at an incredible velocity. In just a few milliseconds, the universe grew from the size of a single atom to that of a football, a truly staggering transformation with profound implications for us today. Cosmic inflation is a key piece of the puzzle, because it helps clarify some of the fundamental characteristics of the universe that we can now observe. For instance, it provides an explanation for the remarkable uniformity of the cosmic microwave background, the residual light from the Big Bang, and for the large-scale distribution of galaxies you see scattered across the sky. Without this inflationary period, the universe might have been a chaotic and irregular place. A fascinating question that often comes up is what occurred after this explosive growth phase concluded. Once inflation ceased, the universe carried on expanding, but at a much more gradual and manageable pace. This slower expansion made it possible for the first particles, atoms, and ultimately the stars and galaxies that we are familiar with to begin forming. Without cosmic inflation, this entire sequence of events might have unfolded very differently, and our present conversation about the universe might not even be happening.
The theory of inflation is not just a compelling idea. It has been reinforced by a wealth of observations and experiments. Key among these is the data collected by the Planck satellite, which meticulously mapped the cosmic microwave background with unparalleled precision. The findings from these studies have lent powerful support to the hypothesis that cosmic inflation was a real event in our universe's history. However, in spite of its many successes, the theory of cosmic inflation still leaves us with some significant unanswered questions. For example, what exactly activated this inflationary energy, and what caused it to shut down? Scientists are actively investigating these puzzles, as the answers could unlock even deeper secrets about the fundamental nature of our universe. It is also crucial to recognize that cosmic inflation is not some static, unchanging idea. As our comprehension grows, new theories and models are constantly being developed. This reality leads to an exciting prospect. What other discoveries about the universe and its origins are waiting for us just over the horizon? The search for answers is ongoing, and every new piece of evidence helps us better understand our place in the cosmos. Some of you might wonder if the concept of cosmic inflation conflicts with the notion of an eternal universe. The reality is that it can actually be compatible with such a model. Inflation might simply represent one phase within a much grander cycle of cosmic expansion and contraction, which opens up a vast landscape of possibilities regarding how everything started and where it is all ultimately headed. As you reflect on the phenomenon of cosmic inflation, it's important to realize that we are standing at the forefront of an incredible voyage of discovery. Each new fragment of the puzzle we solve grants us a clearer perspective on our origins and our collective future. So, the next time you gaze up at the star-filled sky, remember that the story of our universe is infinitely more complex and awe-inspiring than it first seems. The phenomenon of cosmic inflation is merely one of the countless wonders that lie ahead on our magnificent exploratory journey. As inquisitive adventurers of the cosmos, we have the privilege of participating in the quest for answers to fundamental questions, such as what transpired in the universe's initial moments, and how all the matter we observe today could have arisen from that primal event. Our fascinating exploration into the universe's origins reveals the creation of matter and antimatter as a crucial chapter. To begin, you must grasp that at the dawn of time, everything existed as pure energy. Much like water and steam are different states of the same substance, matter and energy are simply two facets of one reality. And as the cosmos began to stretch, this immense reservoir of energy started converting into the particles we know today. Within mere fractions of a second, the circumstances became ideal for matter to form, creating everything you see in the present day. The extreme temperatures and pressures at the instant of the Big Bang filled the universe with a soup of subatomic particles, including quarks, electrons, and neutrinos. As time progressed, these fundamental components started to assemble, with quarks binding to create protons and neutrons, which in turn combined with electrons to build the first atoms, fitting together like pieces of an immense cosmic puzzle. Simultaneously, the Big Bang also produced antimatter, which you can think of as matter's mirror image counterpart, with an equal and opposite particle generated for every particle of matter. A peculiar phenomenon occurred whenever these opposites met. They would instantly annihilate one another, converting their mass back into a burst of energy. Consequently, as the early universe continued its expansion, this process of mutual destruction nearly eliminated all the antimatter that had been created. The slight surplus of matter over antimatter stands as one of cosmology's most profound puzzles. The question of why this imbalance existed continues to fascinate scientists, sparking numerous theories and sophisticated experiments. This fundamental asymmetry is absolutely vital because without it, the universe as we know it, filled with galaxies, stars, planets, and life itself, simply would not exist. The formation of matter following the Big Bang extended beyond just elementary particles. As the cosmos continued to stretch and its temperature dropped, the nuclei of the lightest elements, namely hydrogen and helium, started to take shape. This pivotal stage, known as primordial nucleosynthesis, transpired within the first few minutes of the universe's existence, effectively preparing the foundational materials for all future cosmic structures. With further cooling and clustering, the environment allowed for the formation of complete atoms, which then gathered into massive gas clouds that were the precursors to stars and galaxies. Over vast stretches of time, these clouds collapsed under their own gravitational pull to ignite the first stars. These stellar bodies then served as cosmic forges, creating heavier elements through the powerful process of nuclear fusion, demonstrating that the Big Bang initiated an ongoing evolutionary saga. This perpetual cycle of stellar birth, life, and death enriches the cosmos by dispersing newly created elements across space. It is because of this process that the very atoms composing your body and the air you inhale were originally forged inside ancient stars. To peer into this distant past, modern scientists use powerful particle accelerators to recreate the extreme conditions of the early universe, giving us a direct window into its formative moments. By observing how particles behave under these simulated conditions, researchers uncover vital clues about the universe's greatest secrets. This investigation into matter and antimatter is more than just a scientific pursuit. It invites you to contemplate your own place in the cosmos. Since we are fundamentally made of this matter, its creation story is intrinsically our own origin story. an incredible journey from pure energy that deeply connects us to the cosmic past. This knowledge serves as a powerful reminder that while you may be a tiny component of an immense cosmos, you are assembled from the very same elements forged in stellar cores. The narrative of matter and antimatter reveals a universe governed by a dynamic equilibrium. And with each new finding, we move closer to comprehending its mechanics. This journey of discovery offers a fresh perspective on your role within the intricate fabric of reality, continually enriching and astonishing us along the way. The universe in its initial moments after the Big Bang was a turbulent and intensely hot environment, which raises the question of how the elements we see today came to be. The solution is found in a fascinating process called primordial nucleosynthesis. Though the name seems intricate, it simply explains how the first atomic nuclei were forged in the opening minutes of cosmic history. You can envision it as a vast cosmic kitchen where the basic ingredients like hydrogen and helium were first cooked up. As the expanding cosmos continued to cool, these elemental ingredients started to fuse, creating the first atomic nuclei. This entire creative phase occurred within a remarkably short period, lasting from approximately 3 to 20 minutes after the Big Bang. It was during this fleeting interval that primordial nucleosynthesis produced the cosmic abundance of elements we still observe, about 75% hydrogen and 25% helium. So you might ask why this initial blend of elements holds such significance. The explanation is that these very first nuclei served as the building blocks for all the matter we observe today. Without this fundamental creative phase, our existence would lack water, stars, and even planets, making it a crucial starting point for everything that followed. But what about the other elements, like the carbon and oxygen that are so vital to life? If everything started with just hydrogen and helium, how did they appear? The answer to that question involves the process of stellar evolution. Stars, which formed much later, ignited the fusion of hydrogen into helium within their cores, releasing immense energy and gradually forging heavier elements through nuclear reactions over their lifespans. Essentially, while primordial nucleosynthesis provided the universe with hydrogen and helium, it was the stars that manufactured the elements composing our bodies and the Earth itself. You can picture every star as an elemental factory. Over their entire existence, these cosmic factories generate a wide array of materials that are ultimately scattered into space when the stars conclude their life cycles. This stellar debris becomes the dust and gas from which new stars and planetary systems are born, revealing the universe's endless cycle of creation and destruction. Let's return to primordial nucleosynthesis for a moment. What confirmation do we have that this event actually took place? A primary piece of evidence is the observed proportion of light elements throughout the cosmos. Astronomical studies confirm that hydrogen and helium are vastly more abundant than all heavier elements combined, which strongly supports the theory that primordial nucleosynthesis was a real and foundational cosmic process. This isn't the complete story, however. Primordial nucleosynthesis represents only the opening chapter in a much grander narrative. As the universe carried on with its expansion and cooling, structures of increasing complexity started to take shape. Galaxies, stars, and planets gradually emerged from this initial primordial soup of matter. But consider what might have happened if the universe had begun with different elements instead of hydrogen and helium. The answer could completely alter the cosmic history that we understand. The genuine beauty of science lies in the fact that it always generates more questions than it answers. Primordial nucleosynthesis offers us a model for comprehending how everything originated, yet it simultaneously pushes us to explore even deeper. What do these processes imply for the possibility of life on other planets? Could life even arise in worlds that formed under different conditions? Each time you gaze up at the night sky, I want you to remember that you are witnessing a universe that has experienced an extraordinary journey of creation, evolving from a microscopic point into a vast cosmos teeming with matter and energy. Primordial nucleosynthesis is merely one of many components in this grand puzzle, but it is an indispensable one for making sense of our own position in the universe.
The tale of the elements is also a tale of profound connection. We are all woven into this cosmic fabric, born from material created in the hearts of stars and during the universe's earliest moments. Primordial nucleosynthesis serves as a reminder that while every one of us is an individual, we all share a common origin that binds us together. So the next time you see your reflection, take a moment to consider the atoms that constitute your very being. A portion of these atoms was formed in the intense heat of the Big Bang, while others were forged inside the cores of stars that lived and died long before our world existed. This history, the history of primordial nucleosynthesis, is a potent testament to the fact that we are composed of stardust. And this story is still unfolding. The cosmic microwave background radiation, which is also referred to as the afterglow of the Big Bang, stands as one of the most thrilling discoveries in the entire history of cosmology. But what exactly is it, and what makes it so important? To comprehend this, you need to journey back in time with me to the period just after the Big Bang, imagining a nascent universe that was incredibly hot and dense, where everything we know existed only in a primitive form.
During those first moments, light was unable to travel freely, as if the entire cosmos was enveloped in a thick, impenetrable fog. However, as the universe expanded and cooled over approximately 380,000 years, the conditions transformed. It was at this point that electrons and protons combined to create hydrogen atoms in an event known as recombination, a truly pivotal moment. From that instant forward, light that had been previously trapped was finally liberated to travel across space.
You can envision the universe transforming into an immense ocean of light, where photons were at last able to move without obstruction. This very light, which started its journey so long ago, has been traversing the cosmos ever since. The fascinating part is that when we observe the heavens today, we don't perceive this light as it originally was. Instead, we detect it as microwave radiation, which has been stretched to longer wavelengths by the continuous expansion of the universe. This cosmic microwave background radiation acts as an echo of the Big Bang, a relic from the dawn of the universe that has finally reached us after a journey of billions of years. Some of you may be wondering how we can be certain this radiation is so ancient. The answer is found in our methods of studying the cosmos, using specialized telescopes to capture and analyze these microwave signals. In 1965, two scientists named Arno Penzias and Robert Wilson actually made this discovery by accident while conducting an unrelated experiment, and their work later earned them the Nobel Prize.
If Penzias and Wilson had not been persistent and curious enough to investigate the strange noise in their equipment, our understanding of the Big Bang's scale might have been delayed for years. First, the radiation's temperature of about 2.7 Kelvin gives us solid evidence that the universe has been expanding and cooling since its birth. Moreover, the remarkable uniformity of this radiation indicates that on a grand scale, the early universe was extremely homogeneous, meaning its contents were distributed very evenly in every direction.
However, there are also minute variations within this background radiation that are equally captivating. These slight fluctuations are like tiny wrinkles on a smooth blanket. These incredibly small temperature differences provide us with vital clues about how the large-scale structures in the universe, such as galaxies and galaxy clusters, began to form from the nearly uniform matter of the early cosmos. It seems that every subtle variation in cosmic radiation narrates a piece of the universe's developmental story. The cosmic microwave background isn't merely a faint echo from a bygone era. It serves as a comprehensive map of the primordial cosmos. By examining its properties, scientists can deduce the universe's composition, including the proportions of dark matter and dark energy, forces that remain largely mysterious but are instrumental in the cosmos's ongoing evolution. The value of the cosmic microwave background extends well beyond the act of observation, as it is essential for verifying our foundational theories about the universe's origins and growth. Without this crucial piece of evidence, many of our concepts regarding the Big Bang and the subsequent unfolding of the cosmos would be significantly more challenging to substantiate. You might imagine this cosmic radiation as an ancient manuscript that holds the very secrets of our existence, where every page we decipher brings us nearer to understanding our identity and origins. For much of scientific history, spirited debates surrounded the true nature of the universe, with alternative theories vying against the Big Bang. The confirmation of this background radiation delivered the conclusive evidence that firmly tipped the scales in favor of the Big Bang model. It is as if nature itself preserved a distinct fingerprint for humanity to eventually discover and interpret. Therefore, when you look up into the vastness of the night sky, you are not simply witnessing stars and galaxies as they are now. You are, in fact, peering back in time into a universe that was once unimaginably different, with the cosmic microwave background acting as a direct window to that ancient past. Ultimately, reflecting on the cosmic microwave background serves as a powerful reminder that every scientific discovery inches us closer to unraveling the universe's profound mysteries. This radiation is more than just proof of a critical moment in our cosmic history. It's an open invitation to continue our exploration, to persist in asking questions, and to never lose our sense of wonder at the sheer magnificence of the cosmos. Have you ever been told that the Big Bang was a kind of explosion? This common analogy often conjures images of a conventional blast, similar to a bomb detonating, but it's vital to correct this inaccurate picture. The Big Bang was not an explosion that occurred in space, but was instead the very expansion of space itself. Picture an uninflated balloon. As you fill it with air, every single point on its surface recedes from all the others. This process is a fitting analogy for the workings of the universe. There wasn't a single point of detonation. Rather, there was a universal stretching of space that continues to push galaxies farther apart from one another. The idea of an explosion might be visually compelling, but it fosters significant confusion, as most people associate the term with a destructive event originating from a specific location. The Big Bang, however, wasn't destructive at all. It was the genesis of everything we are familiar with. In the beginning, the universe was incredibly hot and dense, but there was no location where this supposed explosion took place, because all of space was compressed into that singular, infinitesimal point. So, if the Big Bang wasn't an explosion, what is a more fitting description? It helps to think of space and time as an interwoven fabric that is constantly stretching. As the universe expanded, this fabric elongated, and everything contained within it was carried along for the ride. This isn't a scenario where objects are flying apart into a void, but a phenomenon that influences the very structure of the universe itself. Understanding this distinction is critical because it helps you better comprehend the evolution of the universe. It reveals that the cosmos is in a state of perpetual change, in a way being constantly created, as the universe continues to expand every second. This ongoing process is a journey where space and time are linked, in ways we are only just beginning to grasp. When we observe galaxies moving away, they aren't simply objects traveling through an empty expanse. They are integral parts of an expanding cosmic fabric. The light emitted from these distant galaxies is also stretched by this expansion, causing its wavelength to shift toward the red end of the spectrum. This effect is known as redshift, and it stands as one of the most definitive pieces of evidence for our expanding universe. It is truly astonishing to consider that in the initial moments after the Big Bang, the universe was a place fundamentally unlike anything we know. So intensely hot that particles could not even combine into atoms. As the universe expanded and cooled down, however, these particles began to unite, forming the first atoms that would eventually constitute all the matter that exists today. So, how does this relate back to the flawed idea of an explosion? The key lies in realizing that an explosion disperses energy and matter chaotically, whereas the post-Big Bang expansion was a remarkably uniform process. Tiny fluctuations in the density of the early universe were not the result of a chaotic blast, but were instead the seeds from which galaxies and other massive structures would gradually form through a much more subtle and complex mechanism. As we advance our comprehension of the cosmos, it is essential that you discard these simplified images and start to perceive the Big Bang for what it truly is. It represents the very beginning of everything, the singular moment when both time and space first sprang into existence. Characterizing the beginning of our universe as an explosion is a simplistic view that fails to capture the true elegance and intricacy of the cosmos. The expansion of the universe isn't just a theory derived from telescope observations. It's a phenomenon solidly confirmed by the principles of modern physics. Grasping the link between this expansion and the Big Bang is essential for comprehending how the universe has evolved into its current state. When you set aside the notion of a violent blast, you can start to envision a cosmic landscape in perpetual motion and constant transformation. So, the next time you consider the Big Bang, picture a gradual inflation, similar to a bubble gently growing. This bubble isn't merely a three-dimensional sphere. It embodies the very structure of space and time as it expands and develops. In doing so, it gives rise to everything you know and experience in a process that continues right now. Viewed through this lens, the Big Bang transforms into a far more profound and beautiful concept than the simple idea of an explosion could ever convey. We are ultimately discussing the genesis of reality itself, a journey that commenced billions of years ago and persists in unveiling cosmic secrets with every new breakthrough. Understanding the Big Bang, therefore, is not merely about deciphering the universe's origin, but also about discovering your own place within this vast narrative. Gravity stands as one of the universe's fundamental forces, a constant presence in all our lives. Yet, its implications in the cosmic theater are profoundly more complex and captivating. How can a force that seems so straightforward be the architect of the entire structure of existence as you know it? Gravity's influence extends far beyond keeping your feet planted on the ground. It has guided the evolution of the universe from the moment of the Big Bang all the way to the present day. When you typically think about gravity, you probably envision the force pulling you toward the Earth. But have you ever stopped to consider what gravity's role truly is on a universal scale? The answer is that gravity functions as a kind of cosmic cement,
binding together galaxies, stars, planets, and countless other celestial objects in a perpetual, intricate ballet. This fundamental attraction is what enabled the universe to organize itself and evolve from its initial chaotic state. In the moments immediately following the Big Bang, the universe was an incredibly hot and dense environment, where gravity began to exert its foundational influence. As the universe expanded and cooled, gravity's pull started to draw matter together into clumps. This process led to the formation of the very first cosmic structures, like immense clouds of gas and dust, which would later serve as the building blocks for stars and galaxies. Had it not been for gravity, these primordial clusters would never have formed, and the universe might have remained nothing more than a diffuse, featureless mist of scattered particles.
However, the truth is that gravity also operates as a catalyst for chaos. The gravitational pull between particles isn't always a gentle process. It can trigger collisions and mergers, which in turn lead to the creation of entirely new structures. This suggests that the universe did not develop uniformly, but instead evolved through a sequence of dramatic cosmic events, where gravity consistently played the central part. Imagine you are looking at a field of flowers. When one flower bends towards the sun, it is responding to the pull of light. In much the same way, across the immense expanse of the cosmos, stars and galaxies navigate and congregate under the direction of gravity. Yet, gravity's role isn't limited to attraction. It also establishes a delicate balance, which is absolutely vital for the stability of galaxies. Without gravity's steadying hand, stars would simply fly apart, and the magnificent architecture of a galaxy would crumble. Let's now turn to the ultimate destiny of the universe, because gravity not only shapes the present, but also dictates the future. The persistent pull of gravity has the power to slow down the expansion of the universe, which presents a fascinating question about what might happen when all galaxies are moving away from one another. Some scientists propose that gravity could one day overpower the expansion entirely, forcing the universe to collapse in on itself in a cataclysmic event termed the Big Crunch. Is that, however, the only possible outcome? An alternative scenario suggests that the universe might just keep expanding forever. In this version of the future, gravity's influence persists, but it is ultimately overcome by dark energy, an enigmatic force that seems to be accelerating the expansion. This possibility leads to a compelling question. Could the universe expand so much that it eventually becomes a cold, dark, and empty void, where stars burn out and galaxies drift so far apart they disappear from sight? Gravity doesn't just hold matter together. It also directly impacts time itself. According to Albert Einstein's theory of relativity, gravity can actually alter our perception of time. Within intense gravitational fields, such as those found near a black hole, time literally slows down. This phenomenon means that in the vicinity of tremendous mass, the flow of time is different from its passage in areas with weaker gravity, adding yet another layer of complexity to how you understand the universe. When you think about gravity, it's also crucial to consider its connection to other cosmic components, like dark matter. This invisible substance, which you cannot see but whose presence you can infer from its gravitational pull, continues to be a profound mystery that scientists are actively working to solve. What is the specific role gravity plays in the interplay between the visible matter you can observe and the unseen dark matter? This question is not only intriguing, but also vital for understanding how the universe maintains its structure. Furthermore, gravity governs the lives of stars, which are the great elemental forges of the cosmos. It is the force of gravity that ignites the process of nuclear fusion deep within stellar cores, transforming them into factories that produce heavy elements.
Without gravity, stars could not form, and without the stars, life as you know it would be impossible. So, each time you gaze up at the night sky, remember that gravity is the reason those brilliant points of light even exist.
The relationship between gravity and the cosmos is, without question, a deeply compelling subject. Every single day, scientists dedicate themselves to deciphering the many secrets that gravity still conceals, continuing a quest for knowledge that is as vast as the universe itself.
The quest to understand how gravity sculpts the cosmos is ongoing, with every new finding revealing more about our position in the universe. So, the next time you feel gravity's pull, consider that it's more than just the force holding you to the Earth. It is the fundamental power that is sculpted and continues to mold everything in existence, from the birth of galaxies to the eventual destiny of the cosmos itself. Gravity truly is the universal thread that weaves together the entire story of our universe.
What if I proposed that the vast majority of our universe is composed of material we can't perceive at all? It's a captivating thought, isn't it? This idea is the very heart of the concepts of dark matter and dark energy, two of the most profound mysteries known to science. To grasp how these forces shape reality, you first need to understand what they are and how they connect to the cosmic expansion we've talked about. Think of dark matter as a kind of cosmic phantom. While we can neither see nor touch it, its gravitational effects are so significant that we know it must be there. Picture yourself at a party held in complete darkness. You can't see anyone, yet you can feel their presence all around you. In a similar way, dark matter emits no light or radiation, but we can detect its influence in the way galaxies spin and cluster together. The evidence for its existence comes from astronomers observing that stars at the edge of galaxies move far too quickly to be held by visible matter alone, suggesting some unseen mass is providing the extra gravitational grip. And what about dark energy? This is another concept that feels like it has been lifted directly from science fiction. Dark energy is the driving force behind the accelerating expansion of the universe. Imagine you're inflating a balloon. As it gets larger, the surface stretches faster. Dark energy functions in a similar way, pushing space itself apart and causing the universe to expand at an ever-increasing velocity. Its influence is colossal, dominating the universe's total energy budget. So, the natural question is, how do dark matter and dark energy relate to one another? Although both are invisible and mysterious, they perform opposing roles in the grand cosmic drama. Dark matter provides the gravitational scaffolding that allows galaxies and galactic clusters to form and hold together, while dark energy is the relentless force pushing everything apart. It's as if dark matter is a set of strings tying a cluster of balloons together, while dark energy is simultaneously causing those balloons to inflate and drift away from each other.
Let's consider what the existence of these forces means for your understanding of the cosmos. If dark matter and dark energy are this dominant, how does that change our cosmic perspective? Scientists calculate that these two enigmatic components make up about 95% of the universe, which means all the visible matter we know constitutes a mere 5%. This is akin to being adrift in a vast ocean, able to see only the surface, while the immense depths below remain a total mystery. A truly remarkable quality of dark matter is its central role in the formation of cosmic structures. Without it, the galaxies we see today simply wouldn't exist in their current form, as dark matter's gravity was essential for pulling together the ordinary matter that formed stars and planets. The universe would be a far emptier place, likely with very few galaxies or stars, reminding us that what remains unseen can be just as crucial as what is visible.
On the other side of the cosmic coin, dark energy presents us with profound questions regarding the ultimate fate of the universe. If this accelerated expansion continues indefinitely, what does the distant future hold for galaxies? You can envision a scenario where all galaxies eventually recede so far from one another that they disappear from view entirely. The cosmos could devolve into a cold, desolate expanse, where stars burn out and galaxies become isolated islands in an endless void. It's a sobering thought, but also a fascinating one that compels us to push the boundaries of our knowledge. Theories surrounding dark matter and dark energy are constantly evolving as scientists deploy new technologies and construct more powerful telescopes. Each new observation brings us a step closer to solving these cosmic puzzles. Will we ever be able to detect dark matter particles directly? Can we ever truly comprehend the nature of dark energy? These are the questions that fuel the passion and excitement of astronomers worldwide who are on a constant mission to unlock the universe's deepest secrets through everything from laboratory experiments to deep space observations.
With time, our ability to understand these invisible forces will undoubtedly improve, paving the way for new theories and discoveries that could completely reshape our perception of reality. Dark matter and dark energy demonstrate that the universe is perpetually full of surprises, where every solution we discover often gives rise to a new set of questions. It serves as a powerful reminder that science is an endless journey, not a final destination. And each breakthrough challenges us to look beyond the known and question our assumptions. Ultimately, this pursuit of cosmic truth represents one of the greatest adventures humanity can embark on. It's incredible to reflect on how deeply all of this connects to our own existence. By seeking to understand dark matter and dark energy, you are not only learning about the cosmos, but also about your own place within it. We are all an integral part of this immense universe, a universe that is still expanding, evolving, and filled with mysteries that trace their origins all the way back to the Big Bang. Have you ever gazed at the night sky and asked yourself, just how many stars are there in the universe? Providing a straightforward answer is impossible, because the observable universe is staggeringly vast. But the term observable is key here, as it defines the portion of the cosmos from which light has had time to reach us. Beyond the reach of our most powerful telescopes, however, lies a great deal more. The narrative of the Big Bang isn't just a story about our cosmic beginning. It's also a story about everything that lies beyond our sight. To grasp the sheer scale of the cosmos, you can picture our existence inside a colossal bubble. This bubble represents the observable universe, and anything that lies beyond its boundary remains a profound mystery. Because the light from the most distant galaxies has traveled for millions of years to reach our eyes, we are essentially seeing them as they were in the ancient past. Consequently, observing great distances is equivalent to undertaking a voyage through time, a journey that offers us a glimpse into the depths of cosmic history. So what can be said about the universe that we are unable to see? It is at this point that the subject becomes truly captivating. Many astronomers propose that the cosmos may be vastly larger, perhaps even infinite, compared to the portion we can currently detect. Consider how, when you stand on a shore, your view of the ocean is limited by the horizon. Yet, you are certain that the water extends far beyond it. This same principle applies to the universe. Its true size is nearly impossible for us to comprehend, and our instruments reveal only a minuscule fraction of it. This gives rise to a fascinating question. Why does a boundary to our observation even exist? The limitation is a direct consequence of the speed of light. While light moves at an astonishing velocity,
it still requires a finite amount of time to traverse the cosmos and arrive at our location. This establishes a fixed horizon in both time and space that we cannot peer beyond, meaning everything on the other side is, for the moment, completely inaccessible to us. This reality prompts yet another inquiry. Could something else exist beyond our observable bubble? Certain scientists entertain the possibility of other universes in a concept known as the multiverse. You might imagine each universe as a separate bubble in a cosmic ocean, each governed by its own unique physical laws. While this idea is certainly thrilling, it remains entirely theoretical, with no hard evidence to back it up. Still, exploring such concepts helps us to better frame our own existence and the significance of our place in the cosmos. As you and I probe deeper into our own observable universe, we encounter an extraordinary phenomenon: the cosmic microwave background, which is the residual thermal radiation or afterglow from the Big Bang. You can think of it as a faint echo from the distant past, one that provides invaluable data about the conditions of the early universe. This radiation is more than just a piece of the puzzle. It stands as one of the most powerful lines of evidence confirming that the Big Bang actually happened. Another significant question is what comprises all the matter in the universe. Although you see countless stars and galaxies, this visible material accounts for just a small portion of the total mass. The vast majority is an invisible substance referred to as dark matter. You can envision it as a kind of ghost that we cannot see directly, but whose presence has a tangible impact on everything we can observe. Dark matter neither emits light nor interacts with normal matter in familiar ways, but its existence is deduced from the immense gravitational pull it exerts on galaxies. In addition to dark matter, there is another enigmatic component called dark energy, which seems to be the force driving the accelerating expansion of the universe. Picture the cosmos as a balloon that is being steadily inflated. Dark energy acts like the air being forced into it, making it expand at an ever-increasing rate. While we still understand very little about the true nature of dark energy, it holds the key to understanding how our universe will ultimately evolve in the distant future. Our deeper exploration of the observable universe inevitably leads us to ask if life exists on other worlds. The ongoing search for exoplanets within habitable zones suggests that there could be a great number of planets similar to our own. However, the distances separating these potential worlds from us are simply staggering. If you tried to send a message to even the nearest star, it could take many years or possibly centuries to arrive. The sheer vastness of space is a constant reminder of how isolated we might be in this immense cosmos. Contemplating the evolution of our universe also raises profound questions about its ultimate destiny. Will it continue to expand forever, or will expansion eventually halt and reverse into a cosmic collapse? These questions remain at the heart of the cosmological mystery. Some theories propose a future Big Crunch, where all matter falls back into a single point, while others predict an endless expansion, leading to a universe that grows progressively colder and emptier. The Big Bang is therefore not merely a tale about the origin of everything. It serves as the essential starting point for our exploration of the vast and puzzling universe laid out before us. By working to understand the Big Bang and the limits of our observable cosmos, you and I can begin to grasp our own place within this gigantic cosmic bubble. This process of reflection encourages us to acknowledge our own innate desire for knowledge. Ultimately, every question we pose unlocks new avenues for exploration and new potential for discovery. What other enigmas are waiting to be uncovered in the boundless ocean of space? The quest for understanding has no end, as each answer we find seems to generate a host of new questions, pulling us ever deeper into the heart of the universe.
When you look up at the night sky, have you ever felt a sense of wonder? Every single one of those stars is its own world, and each has followed a remarkable path since its formation.
But this leads us to wonder how galaxies actually come into being and what function they serve in the universe's grand narrative. The history of galaxies traces back to the initial moments following the Big Bang, when the entire cosmos was a realm of extreme heat and density. Think of this early universe as a sprawling ocean, initially filled with churning bubbles of energy and particles in a rapidly expanding space. As this cosmic ocean cooled, the fundamental force of gravity, which acts like a relentless, invisible magnet, began to pull these particles together, forming the first tiny droplets of matter that would one day grow into the galaxies you see today. The very first galaxies materialized from these cosmic clusters, weaving an immense tapestry of dust and gas across the universe's canvas. But just how much time did a galaxy's formation require? The answer isn't simple, as it seems the earliest galaxies started to coalesce several 100 million years after the Big Bang. In that era, the universe was in its infancy, and the light from the first newborn stars was only just beginning to pierce the pervasive darkness. Much like the first glimmer of dawn on a vast desert horizon, offers only a hint of the day to come.
Galaxies are not static objects. They are in a constant state of flux and evolution. Under the relentless influence of gravity, these developing galaxies can merge, giving rise to even more massive structures. This process is akin to assembling an intricate puzzle, where each merger adds complexity, eventually forming immense galaxy clusters and superclusters, which can be thought of as vast galactic families gravitationally bound to one another. Within these galaxies, a perpetual cycle of stellar birth and death unfolds. But how, exactly, do stars come to be in the heart of a galaxy? It begins when enormous clouds of gas and dust start to collapse under their own gravitational pull. This gravitational collapse causes a dramatic increase in both temperature and pressure at the core, and at the zenith of this process, a new star ignites. You can picture it as building and lighting a fire. You first gather the fuel, then provide the spark, and from that ignition, both light and heat radiate outward. Stars contribute far more to the universe than just illumination. They function as cosmic element factories. Deep within their cores, they sustain nuclear reactions that forge heavier elements, including carbon and oxygen. When a star reaches the end of its life, whether through a colossal supernova explosion or by collapsing into a white dwarf, it ejects these elements back into the cosmos. In doing so, stars enrich the interstellar medium, supplying the fundamental materials for new stars, planets, and ultimately, for life itself. Galaxies also manifest in a wide variety of shapes and sizes, with some appearing as spirals, like our own Milky Way, while others are elliptical or have irregular forms. This diversity is a direct consequence of their unique histories of formation and evolution. Spiral galaxies, for instance, are characterized by rotating arms where new stars are actively forming, whereas elliptical galaxies are generally more ancient, composed primarily of old stars that have long since depleted their nuclear fuel. A truly captivating aspect of galaxies is that they rarely exist in isolation. The majority are found in groups or clusters, where the force of gravity acts as the cosmic glue holding them together. These interactions, however, are not always peaceful. Galaxies can collide and merge in what become extraordinary cosmic spectacles. Imagine two massive freight trains colliding at full speed. The impact unleashes a tremendous explosion of energy and matter, and a similar process unfolds on a galactic scale in space. The evolution of galaxies is far from over. As the universe continues its relentless expansion, galaxies are steadily moving farther away from one another.
This cosmic recession stands as one of the most powerful pieces of evidence supporting the Big Bang theory. In the immense depths of this cosmic ocean, galaxies are like vessels drifting apart, growing ever more distant. Yet all of them share a common point of origin in their history.
The narrative of galaxies is not merely a chronicle of formation and collisions. It also informs us about our own position within the cosmos. Every single star you observe in the night sky serves as a reminder that we are an integral part of an incredibly vast and ancient universe. Galaxies are our cosmic neighbors, and by investigating their evolution, we gain insights not only into the universe's past, but also into our own collective future. So, the next time you find yourself gazing up at the stars in wonder, it is a unique story, a distinct chapter in the great book of the universe. The evolution of galaxies stands as a testament to the profound beauty and complexity that envelops us. And it extends an open invitation for us to continue exploring and uncovering the mysteries of the cosmos. What truly occurs on this immense cosmic stage when a new star is born? The life of a star is a captivating journey, filled with transformations and cycles that mirror the destiny of the universe itself. From its initial formation to its eventual demise, every star narrates a story that helps us comprehend how the vast cosmic web was constructed. Stars are born inside gigantic clouds of gas and dust, which are known as nebulae. You can think of these clouds as enormous cosmic incubators, where the precise conditions for stellar birth are cultivated. But what initiates this process? When specific regions within a nebula achieve sufficient density, gravity begins its work, drawing in more and more material, which in turn elevates the pressure and temperature at the very center. This is the crucial moment when nuclear fusion ignites, the very pulsating heart of a star. At this juncture, the star enters what is known as the main sequence phase, a stage where it will spend the vast majority of its existence. For billions of years, the star will steadily burn hydrogen, converting it into helium through the process of nuclear fusion. This reaction not only generates the light and heat we can perceive, but also maintains a delicate equilibrium between the inward crush of gravity and the outward pressure created by the nuclear reactions in its core. Can you even begin to imagine an environment where temperatures soar beyond millions of degrees? Eventually, over immense timescales, the star depletes its primary supply of hydrogen, and at this point, its life takes a dramatic new direction. The internal pressure is no longer sufficient to counteract gravity, and the star begins to collapse in on itself. This collapse, however, is not an end, but rather the start of a new phase. Temperatures in its core skyrocket to a point where helium can begin to fuse into heavier elements, like carbon. In this way, stars serve as cosmic factories, creating the very elements that are the foundation of everything we know. But what takes place when a star has finally consumed all of its available fuel? The most massive stars undergo a spectacular detonation known as a supernova. This single event is so incredibly powerful that it can momentarily outshine an entire galaxy. The energy from a supernova scatters all the elements forged within the star across the surrounding space, effectively seeding new generations of stars and planets. Did you know that the very elements composing your body, such as carbon and oxygen, were originally created inside stars that exploded billions of years ago? In contrast, smaller stars conclude their existence with far less spectacle, transforming into white dwarfs. Following their supernova phase, these celestial bodies cast off their outer envelopes, exposing a searing core that gradually cools over eons. What remains is a stellar ember, a remnant capable of enduring for trillions of years, representing not an ending, but a new chapter, as its scattered elements provide the raw material for the next generation of stars and planets.
The story of a star involves more than just its birth and demise. It is also defined by how it interacts with its cosmic neighborhood. Many stars exist in binary or multiple systems, where at least two stars are gravitationally bound, orbiting one another and exchanging matter and energy. This mass transfer can trigger extraordinary events like novae, in which a white dwarf siphons material from its partner star, igniting a brilliant flash of light in a true celestial ballet.
Stars also serve as the primary architects in the construction of galaxies. As countless stars are born, age, and eventually perish, they congregate into immense galactic structures which house billions of stars alongside vast clouds of interstellar gas and dust. The gravitational interplay between stars and this surrounding medium is what ultimately sculpts galaxies and guides their development through cosmic time. But you might wonder what occurs when two galaxies collide. Such galactic mergers are actually frequent occurrences in the cosmos, often triggering bursts of new star formation and completely reshaping the galaxy's structures. On a more local scale, the stellar life cycle is what dictates the creation of solar systems, because when a star expires, its enriched material is ejected into space. This matter can then be integrated into other nebulae, eventually coalescing to form new stars, planets, and perhaps life itself. This unending cycle of creation, destruction, and renewal is an eternal dance that showcases the dynamic essence of the universe. When you consider the timescale, a star's life can span millions or even billions of years, offering us a profound look into cosmic history. The most ancient stars identified are over 13 billion years old, meaning they have been silent observers of the universe's evolution almost since its inception, acting as cosmic fossils that narrate the epic of our cosmic home. So, what is the significance of all this for you and me? Grasping the life cycle of stars helps us comprehend our own position within the universe. We are fundamentally the products of stellar generations that formed, lived, and died, forging the very elements that constitute our bodies. Each time you gaze up at the night sky, you are witnessing the legacy of these ancient suns, a powerful reminder that you are part of a cosmic pattern vastly larger than yourself. The life of a star is a remarkable odyssey that mirrors the history of both the universe and our own existence. As we investigate how stars form, evolve, and ultimately meet their end, we forge a connection with the immense and intricate web of reality. Every single star is a chronicler of cosmic history, and in observing its light, you are reminded that you are woven into a grander story, a part of the very fabric of spacetime. What is the ultimate destiny of the universe? This is a question that has captivated scientists and philosophers for ages. The realization that everything we perceive, from the most brilliant stars to the planet we inhabit, had a beginning, naturally compels us to contemplate its conclusion. While the Big Bang Theory provides a glimpse into that origin, it also encourages us to speculate on what the distant future holds. One initial scenario to consider is a universe that expands forever. You can picture the cosmos as a perpetually inflating balloon, where with every passing moment, the galaxies drift further apart as space itself stretches. Should this expansion persist without end, the universe will steadily cool down. Stars will exhaust their nuclear fuel and cease to shine, and in time the cosmos will devolve into a vast, frigid, and empty expanse, an eternal, icy silence. Alternatively, there is the concept of the Big Crunch. Although the universe is expanding now, what if that expansion were to someday halt and then reverse?
In this outcome, the cosmos would start to collapse back in on itself, much like the balloon from before deflating. Everything you know could reconverge into a single, infinitesimal point, not unlike the one that preceded the Big Bang, perhaps heralding a cosmic rebirth in an endless cycle of expansion and contraction.
Yet, a third possibility, known as heat death, has attracted significant attention. This theory proposes a future where the universe achieves a state of perfect thermodynamic equilibrium. Energy would become so uniformly distributed that no further reactions could generate light or heat, causing all stars to extinguish and galaxies to dissolve. In such a universe, time itself would become meaningless, with no events to distinguish one moment from the next. A cosmos frozen in unchanging stasis. One of the most fascinating factors in these predictions is dark energy, a mysterious force that seems to be accelerating the universe's expansion. If its power continues to escalate, it could propel the cosmos into a future where expansion becomes so rapid that galaxies recede from one another at the speed of light. In that scenario, even the closest stars would vanish from your sight, leaving the universe a profoundly lonely and dark domain. Confronting these possibilities raises deep questions about our own significance. If everything we cherish is destined to dissolve into a cold void, what is the point of our existence? Yet there is a certain freedom in this uncertainty. It implores you to value every single moment, to appreciate life, and to build meaningful connections within a universe that, for all its vastness and ambiguity, is also breathtakingly beautiful. Confronting these possibilities raises deep questions about our own significance. If everything we cherish is destined to dissolve into a cold void, what is the point of our existence? Yet there is a certain freedom in this uncertainty. It implores you to value every single moment, to appreciate life, and to build meaningful connections within a universe that, for all its vastness and ambiguity, is also breathtakingly beautiful. Ultimately, theories about the future of the cosmos teach us that our time is an exceptionally precious commodity. Each star that glimmers in the sky, every planet that circles it, and every moment that you experience are all threads in a magnificent, though uncertain, cosmic tapestry. The grand story of the cosmos mirrors your own life, as each choice and event you face weaves a distinct personal history. It's truly incredible to consider that regardless of what the future holds for us, the universe itself has weathered billions of years of constant flux. This epic tale of cosmic creation and development serves as a powerful reminder that while an end might be certain, the profound significance is found within the journey itself. So you might ask, what does the future have in store? As you search for answers, it's crucial to hold on to the fact that you are an integral piece of this immense universe. Though your actions may seem minor against the vastness of space, they create ripples that affect your immediate world. The way you look after our planet, nurture your connections with others, and contribute to your community is what ultimately gives your life its deepest meaning. Accepting your fleeting existence within a perpetually evolving cosmos can motivate you to live a more purposeful life. Every sunrise presents a fresh chance to create something significant, be it through scientific discovery, artistic expression, or the simple acts of friendship and love. While the ultimate destiny of the universe remains a mystery, it is your personal experiences and the bonds you form that truly shape your humanity. As you travel through time and space, keep in mind that every conclusion can also serve as the start of something new. Much like the Big Bang gave rise to a universe brimming with life and potential,
Your own existence is rich with chances for personal growth, education, and discovery. Doesn't that alone give you a reason to cherish each day you spend in this magnificent cosmos? This brings us to the fascinating and often bewildering concept of time itself. Whenever the Big Bang is mentioned, you might naturally question what came before that pivotal instant. Was it a complete void, or did something else occupy reality?
In reality, contemporary scientific theory suggests that even asking about a time before the Big Bang is fundamentally illogical. While this may sound peculiar, allow me to help unravel this mystery with an analogy. Picture time as a great river. The Big Bang in this scenario represents the very source where the river originates. Prior to that point, there was no river, and by the same token, there was no time as you understand it. To put it simply, the Big Bang marks the absolute beginning of time itself. This concept can be challenging to accept, as you are likely conditioned to perceive time as a constant, uninterrupted flow that has always been present. However, to understand this context, you must recognize that time and space are woven together as a single, inseparable fabric. For a moment, envision space as a blank sheet of paper. If you were to crumple it, you would create creases and distinct sections that, despite appearing separate, are still part of the whole. Now, before the Big Bang, this sheet of paper, and therefore space itself, did not exist. Everything familiar to you, from stars and planets to the emptiness between them, sprang into being at that singular genesis. Trying to conceive of what came before is thus akin to asking what you would find past the boundary of something that isn't there. What then does this imply for your perception of the cosmos? It suggests that your very notion of time is a direct result of the universe's own development. Time started to acquire its familiar properties only as the universe expanded and its temperature dropped. Consequently, the question of what happened before the Big Bang is not just unanswerable, it is also inherently misleading, as you cannot search for a moment that precedes the very beginning of existence. Certain hypotheses propose that our universe isn't a one-time occurrence, but rather an element in a much larger, recurring cycle. Even within these frameworks, however, the idea of before poses a significant challenge. If you visualize the universe undergoing phases of expansion and collapse, every new cycle would still commence with a Big Bang, meaning time would restart from that point in each iteration. It's fascinating that while countless cultures and schools of thought have pondered the origins of time and the universe, modern science presents a view that directly confronts your natural instincts. You shouldn't picture the Big Bang as an explosion happening within an already existing void. Instead, you must grasp it as the very genesis of space and time themselves, a core principle that shapes how contemporary cosmology investigates fundamental questions of being. An alternative way to conceptualize this is by thinking of a balloon. As you blow air into it, you are actually creating and expanding the volume within its walls. The instant you start inflating it, the internal space comes into being. Prior to that, no such space existed. There was only the latent potential of the material itself. In the same way, the Big Bang serves as that critical juncture that brought forth the entirety of our known reality. It's only natural for your mind to jump to further questions, such as what might occur if the universe ceases to expand, or if it all collapses back on itself. These are compelling thought experiments, but they don't alter the fundamental concept that, based on our present knowledge, time originated with the Big Bang. While you can hypothesize about events yet to come, the pre-cosmic past remains a domain where science faces distinct boundaries. Your curiosity is a boundless force, driving a desire to comprehend things that are invisible or beyond your full grasp.
This leads some to contemplate the possibility of other universes or dimensions existing prior to our own. Yet, in the absence of tangible proof, such notions are confined to the realm of speculation. Science is built upon a foundation of observation and hard evidence, and as of now, no data exists to validate any concept of time before the Big Bang. You should keep in mind that the Big Bang represents more than a singular event. It is a powerful concept that provides a structure for comprehending the universe's evolution. It gives you a framework for contemplating the interplay of time, space, matter, and energy. As you delve deeper into its consequences, you'll find that every new finding prompts further questions, though always constrained by the boundaries of what is observable and knowable. Therefore, the next time your thoughts drift to what could have existed prior to the Big Bang, remind yourself that the true focus isn't on a before. Instead, it lies in the continuous, magnificent expansion of the very universe you inhabit right now. The great appeal of cosmology is that while some questions may always linger, every new finding brings you closer to grasping your own existence and the immense cosmos around you. The question of whether alternatives to the Big Bang exist captivates both scientists and enthusiasts, inviting you into a world of fascinating possibilities. Although the Big Bang is the most widely accepted explanation for the universe's origin, it's vital to recognize that it is not the only theory being considered, as science is in a constant state of evolution, where new information can reshape our ideas.
One notable alternative is the steady-state theory, which asks you to envision a universe that has perpetually existed in a state similar to what you see today, expanding eternally without a distinct origin point. In this framework, as galaxies separate, new matter spontaneously emerges to form new galaxies, maintaining a consistent cosmic density. Despite its appeal, this concept has lost significant traction over the last few decades because of compelling evidence supporting the Big Bang, such as the discovery of cosmic microwave background radiation.
Another compelling idea is the multiverse theory, which poses the question, what if our universe is merely one within an enormous collective of separate universes? This concept suggests that our Big Bang was just a single event among countless others, each occurring in its own bubble of spacetime. Every one of these universes could operate under its own set of physical laws, giving rise to an endless spectrum of realities. As intriguing as this idea is, it presents the profound challenge of how you could ever experimentally verify the existence of these other realms. A different perspective comes from quantum relativity theory, which proposes that the universe might have originated from quantum fluctuations within a primordial vacuum. You can picture this as a vast ocean of potential, where a single bubble suddenly materialized, laying the groundwork for our cosmos. In this scenario, the Big Bang wasn't a one-time event, but rather an element of an ongoing cycle of creation and annihilation at the quantum scale, a theory that remains in development and currently lacks conclusive proof. The cyclic model offers yet another intriguing possibility for the universe's history. Instead of having a definitive start and finish, this theory suggests the cosmos undergoes endless cycles of expansion and contraction. Imagine it as a giant spring that repeatedly stretches and compresses, with each collapse triggering a new Big Bang. This suggests that the universe you inhabit is just one phase in an infinite sequence, though the model struggles to align with current observational data. A lesser-known concept is the modified gravity theory, which challenges the assumption that gravity operates uniformly across all cosmic scales. It proposes that gravity's behavior might change under different conditions, which could reshape your understanding of the universe's evolution and provide an alternative to the Big Bang model. However, this idea requires substantially more research before it can be validated. Each of these alternative frameworks presents a unique story about the origin of everything. But you might wonder how they hold up against the Big Bang theory. The reality is that most of these concepts currently lack the robust empirical backing that the Big Bang model has accumulated. Nevertheless, the scientific community continues to vigorously explore and debate these ideas, always searching for new data that might lead to more definitive answers. This leads you to question whether the Big Bang and its alternatives must be mutually exclusive. It's possible that in the future you will find that the Big Bang is actually one part of a much larger narrative, where other theories serve as complementary pieces of the cosmic puzzle. Scientific progress often comes from weaving different concepts together into more comprehensive frameworks that deepen our understanding. So, you are left to ponder whether the Big Bang is the conclusion of the story or merely its opening chapter. The answer is likely to evolve as our grasp of the cosmos expands. Ongoing and future research could yield unexpected insights, perhaps even merging the Big Bang with aspects of these other theories to forge a more complete model of the universe's birth and development. Ultimately, the pursuit of cosmic knowledge is a journey to understand your own origins. By investigating these alternatives, you are not just trying to comprehend the universe, but also your own place within its vast expanse. It is human curiosity that compels you to ask these questions, to explore, and to uncover what is new, pushing the boundaries of science ever further. The primary lesson for you in all of this is that science is never static. It is a dynamic process that evolves with every breakthrough. Theories that are considered fringe alternatives today could become the cornerstones of cosmology tomorrow. On this voyage into the unknown, every question you ask is a step toward a more profound comprehension of the universe and of yourself. The scientific consensus around the Big Bang theory resembles a complex puzzle assembled over many decades. As researchers uncovered new evidence, the image of the universe's origins grew clearer and more persuasive. To understand this, you have to look at the story of its acceptance, which is filled with surprising twists and fascinating details. One of the foundational pieces of this puzzle came from astronomer Edwin Hubble's observations in the 1920s. Hubble revealed that galaxies are receding from us, and the more distant they are, the faster they are moving away. This discovery was a profound clue. If all galaxies are moving apart now, it strongly implies that they must have been much closer together in the past, suggesting a common starting point for the entire universe. But what did this observation truly signify? It prompted scientists to entertain the notion that the universe has not always existed in its current state. The concept of everything originating from a point of extreme heat and density was revolutionary, and the scientific community was far from unified at first. In the beginning, many scholars favored the idea of a static, eternal universe, which begs the question, how did the Big Bang eventually convince almost everyone it was the right answer? The discovery of the cosmic microwave background radiation marked a decisive moment for the Big Bang theory's validation. Back in 1965, a persistent microwave signal that seemed to emanate uniformly from every direction in the sky was accidentally detected by Arno Penzias and Robert Wilson. After careful analysis, they understood this phenomenon was concrete proof of the Big Bang, an ancient echo from that foundational moment, forever imprinted upon the cosmos. It's a remarkable thought, isn't it, that you and I can still listen to a faint whisper from the very birth of reality. As time went on, an increasing body of evidence began to accumulate in support of the theory. Another critical piece of the puzzle came from primordial nucleosynthesis, which describes the formation of light elements in the initial minutes following the Big Bang. Researchers calculated the expected abundance of hydrogen,
helium, and other light elements that should have been created, and when these predictions were compared with astronomical observations, it provided another powerful confirmation of the theory's validity.
This led the scientific community to gradually embrace the Big Bang not merely as a hypothesis, but as a reality, strongly supported by observable data. However, the road to accepting the Big Bang theory was far from straightforward, as it was met with considerable resistance and skepticism. In their search for alternative explanations, some scientists proposed other models, such as the oscillating universe, which posits an endless cycle of cosmic expansion and contraction. Yet, as more and more observational evidence was gathered, the Big Bang theory grew progressively stronger and more difficult to dispute. The theory also gained immense strength from the collaboration across various scientific disciplines. Physicists, astronomers, and cosmologists worldwide joined forces to deepen their comprehension of the theory's implications. Particle physics, for instance, supplied the essential framework for understanding the processes at play during the universe's earliest moments, making the picture of the Big Bang clearer with each new finding. But what can be said about the questions that continue to elude us? You see, embracing the Big Bang theory doesn't imply that every puzzle has been solved. The scientific community is still actively investigating and pursuing answers to profound questions, like the true nature of dark matter and dark energy. These elements represent pieces that don't yet fit perfectly into our understanding of the cosmos, suggesting the Big Bang might only be one chapter in a much larger story we have yet to uncover. Historically, the journey to the Big Bang theory's acceptance has been a thrilling saga of intellectual pursuit. Every step was pivotal, from the initial glimmers of observational data to the technological breakthroughs that empowered new lines of inquiry. And while the theory has robustly withstood the test of time, it is our innate human curiosity that compels us to keep seeking answers. Ultimately, this quest to comprehend our own place in the vastness of the universe is a defining aspect of what it means to be human. At its heart, the narrative of the Big Bang is a tale of discovery that invites you to question, to explore, and to stand in awe of the cosmos's grandeur. The theory's acceptance has not only reshaped our view of the universe, but has also underscored the vital importance of evidence and scientific collaboration. Reflecting on this journey reminds us that every discovery is a leap forward in our collective pursuit of knowledge, in a universe teeming with mysteries yet to be solved. Did you know that while the Big Bang theory stands as one of the most compelling explanations for the origin of the universe, it is also surrounded by a host of fascinating questions? As we delve into the secrets of the cosmos, certain inquiries emerge that, despite their apparent simplicity, ignite a sense of wonder in nearly everyone. Let's explore some of these common questions about the Big Bang and provide clear and engaging answers. One of the most frequent questions people ask is, what exactly occurred in the instant right after the Big Bang? To grasp this, you can try to picture the entire universe compressed into an infinitesimally small point. In that fraction of a second, everything you know, including space and time themselves, began to expand at a rate that is truly beyond imagination. The evidence for this event is found in the cosmic microwave background radiation, which acts as a lingering echo of the Big Bang that we can still measure today. Another captivating question is whether the universe is continuing to expand. The answer to that is an emphatic yes. A helpful analogy is to think of the universe as a balloon that is constantly being inflated. As it fills with air, any points drawn on its surface will naturally move farther apart from one another. This is a simplified model of how galaxies are receding from each other, a phenomenon that was confirmed through various observations, notably by the astronomer Edwin Hubble during the 20th century. People often refer to the Big Bang as an explosion, but you might wonder if that description is accurate. This common confusion stems from the term explosion itself. In truth, the Big Bang was not a detonation that happened at a single location in space. It was instead an expansion of space itself. Imagine every part of the universe moving away from every other part simultaneously, rather than debris flying out from a central point. So while we use the word, it wasn't an explosion in the conventional sense. The concept of the initial singularity is another truly mind-bending idea. To put it simply, this refers to the state of the universe at the very moment of time zero, before the expansion started. The singularity remains a profound mystery because the laws of physics as we currently understand them are insufficient to describe what was happening at that instant. It is much like trying to understand what is on the other side of a locked door. You know something is there, but you are unable to see what it is. Finally, the theory of cosmic inflation is a concept that has completely transformed our understanding of the Big Bang's earliest moments. But what precisely does it entail? This idea suggests a period of incredibly rapid, exponential expansion that took place just a fraction of a second after the initial event, providing explanations for many of the universe's observed properties. Consider the idea that, in its initial fractions of a second, the cosmos underwent a period of faster-than-light exponential growth. This incredible burst of expansion, known as inflation, accounts for many of the universe's features, including why it appears so uniform across immense distances. Without this event, explaining the present-day appearance of the cosmos would be a profound challenge. Another puzzle stemming from the Big Bang involves the relationship between matter and its counterpart, antimatter. The central question is why matter dominates the universe today. In the earliest moments, they were produced in almost identical quantities. Yet something allowed matter to persist while nearly all antimatter was destroyed, a fundamental asymmetry that remains one of the greatest unsolved problems in contemporary cosmology. Next, you have the crucial process of primordial nucleosynthesis. Within the first few minutes of the universe's existence, the very first atomic nuclei were forged, creating the lightest elements like hydrogen and helium. It was as if the cosmos was composing its foundational recipe for matter. And this initial blend of elements set the stage for the later emergence of stars and galaxies. Think of the cosmic microwave background radiation as a quiet observer of ancient history. Its significance cannot be overstated, as this faint glow is the afterglow of the Big Bang itself, an echo of light that has stretched and cooled with the expansion of space. Uncovering this relic radiation was a monumental achievement because it offered concrete proof that the Big Bang was a real event. This naturally leads you to wonder, what might exist beyond the edges of the observable universe? The honest answer is that we simply don't have a definitive answer. The portion of the cosmos we can see is just a tiny fraction of what might truly be out there, similar to being in a pitch-black room and only perceiving what a single window reveals. Everything outside that limited view continues to be a profound mystery. You might also ask whether anything existed prior to the Big Bang. According to our current scientific understanding, time itself originated with the Big Bang, which means the concept of a before doesn't apply in the way we normally think of it. You could say that the universe's clock only began to tick at that very moment, which forces you to challenge your fundamental assumptions about the nature of time itself. While other concepts, such as the steady-state theory, have been put forward, the vast majority of current evidence points to the Big Bang as the leading explanation for cosmic origins. However,
Science always remains receptive to new discoveries and evidence that could emerge down the line. As you navigate the immense ocean of the cosmos, it's essential to continue questioning and exploring, as this forges a deeper connection to the universe you inhabit. The subject of the Big Bang is fascinating, but it's often clouded by misconceptions. This event isn't just a distant story about cosmic origins. It's a window into our deepest past. Happening around 13.8 billion years ago, it set in motion the existence of everything: time, space, and the very matter that forms our world, allowing you to better grasp the cosmos's intricate nature.
So what is the real-world impact of this ancient history on your life today? The stars you observe at night are direct descendants of the primordial matter forged in that initial event. Every single element that constitutes your body, from the carbon in your cells to the oxygen you inhale, can be traced back to processes that began in those first few moments of existence. Contemplating the lives of stars raises an intriguing parallel: the relationship between our own life cycles and theirs. Stars are born, live for billions of years, and eventually die, a pattern not unlike the cycles of life on Earth. In their final moments, massive stars explode as supernovae, scattering newly forged elements across space, elements that will form the next generation of stars, planets, and ultimately, you. The universe's ultimate destiny is another captivating subject. The Big Bang initiated a path of relentless expansion, but where is it all leading? Some cosmological models predict this expansion will go on forever, while alternative theories propose a future collapse. This ambiguity about the cosmos's final chapter encourages you to ponder your own place in this grand, unfolding narrative. Venturing into alternative cosmological models is a fascinating exercise. Some hypotheses propose that the universe undergoes endless cycles of expansion and contraction, while others posit the existence of multidimensional realities. While these concepts are intellectually stimulating, the broad scientific consensus on the Big Bang provides a firm grounding for you to continue exploring and comprehending our cosmos and your unique place within it. Your innate human curiosity is a boundless force, and for generations, the Big Bang has been a focal point for our deepest questions and theories. This quest to understand where everything came from has been a relentless pursuit, linking ancient thinkers with today's researchers in a single, continuous journey of discovery. As science advances, it dismantles old myths and presents fresh viewpoints. Yet this progress only opens up more space for your curiosity to explore what mysteries still lie ahead. Concrete evidence, like the cosmic microwave background radiation, offers you a tangible link to the Big Bang itself. This faint afterglow from the dawn of time provides a direct window into the universe's infancy, allowing you to observe the conditions of its very first moments. Every discovery of this nature provides another crucial piece of the cosmic puzzle, highlighting the intricate elegance and vast complexity of the universe around you. Ultimately, comprehending the Big Bang is more than a scientific exercise. It's a profound invitation for you to contemplate your own existence. It serves as a powerful reminder that you are part of something immeasurably vast, and that your personal story is deeply woven into the very fabric of the universe's timeline. Each star you see in the night sky acts as a luminous link to this primordial past, while also illuminating the path into the future. The true value in grasping the Big Bang is found in its power to ignite your sense of wonder and fuel your drive to learn more. By replacing old myths with a lucid understanding of this theory, you not only broaden your knowledge,
but also cultivate a much deeper and more meaningful connection with the cosmos. It enables you to truly appreciate the spectacle of the universe and to recognize the role you play within its grand design.
So, the next time you gaze at the stars and ponder the universe's origins, remember that each question you pose and every answer you find moves you closer to understanding your place in this immense and breathtaking cosmos. On this voyage of discovery, your curiosity is the most valuable guide you have. The greatest adventure is only just getting started, and you have to wonder what secrets the universe will unveil to you next.